Sorry, I hope I didn't have to cut off anything, but this was 13 seconds over. I hope YouTube isn't mean, but it has been very mean. So, I don't know. So, we've enumerated, so this are all our possibilities, and they're all disjoint possibilities. So, remember, third law of probability, disjoint events. The probabilities sum up. And since we just showed all disjoint events, probably should sum up to 1. So if you saw this as a sum, probability of k equal, from k equals, you can have 1 of that guy, up to n. This sum, we have to prove that equals to 1. That's very simple, very simple. Just rewrite this, and then it's going to cancel. It's okay. You should be able, this is a bread and butter proof. Just straightforward computation. So that is binomial distribution. Next thing we have is geometric progression, the geometric distribution. Wait, why it's called that? Think about geometric progression. You'll see in the formula. So we keep on flipping a coin. Flipping on flipping until it lands on heads, and then we stop. What is the possibility of it? What's the possibility? What is all the sample space? What is all the possible outcomes of this experiment? Well, the head can land once, and then we're done. It could take 2 times. It could take infinite number of times. It may never happen in this crazy universe of ours. So, the way we see this, probability that it takes first time and that it succeeds, let's say it's going to be P. But if it fails, it's going to take, the probability of taking 2 times is 1 minus P times P. And we can see inductively. And we actually prove inductively. But you know, some things in induction is so trivial. You can see it. And you can actually show it trivial proof. But don't worry. Unless you're in a mathematical audience, you must prove via induction. But yeah, just you can see it. But it will be simple proof. We can see that inductively, the time that each k, the probability that that the experiment will end on the kth heads, they will take k times, is, remember, we need 1 minus p to the k failures. Because remember, when we draw out probability chart, we need all these guys to fail. So fail, 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 success. Then we need, and at the very end, we need 1 success. And that's P. So, remember, once again, these are disjoint events. Axiom number 3, we always refer to the axioms. And also, entire space, probability of S has to equal to 1. So this guy, the sum of all these possibilities, 1 minus k, from k equals 0 to infinity, has to equal 1. Now, the reason why it's called geometric is because you can think of this as a geometric progression. Pull this guy out. Sum this guy. 1 over 1 minus p. Yeah, and you can, and it's going to cancel. And it's going to end up being 1. Yeah, it could work. Well, actually, this should be 1, shouldn't it? And then I have to probably divide. Yeah. So that is good. Next thing. So if you saw this as a PMF, the space of all its probability, and we're enumerating it, 1, 2, it should look like this, because you remember, we're multiplying by by values between 0 and 1 makes things smaller. So it's gonna get smaller. So, what else is there to talk about? Poisson distribution. Now, Poisson distribution is a little bit difficult. But the thing is, just think of it as a model. It actually fits many models, many models. So let's define it as a probability that the cave will be successful. You know what? I should try to write it out first. I haven't done this in a year, even though probability was my favorite subject. Lambda to the k over k factorial. Is that right? No. You need an e to the minus lambda k to cancel it. Yes. Let me check. E to the minus lambda. Is it recording? It is recording. Yes? No. Right there. I've done this many times, my friend. Yes, this will make sense because when you sum this up from k equals 0 to infinity, this guy is going to be turned into e to the lambda. Remember, so we're going to model this. The probability that you succeed on the kth time. Kth success. Probability is this guy. Remember, this guy is strictly between 0 and 1. And also, when you sum this guy, k factorial e to the minus lambda equals e to the minus lambda times e to the lambda equals 1. Remember, you should know this. Summing lambda to k over k factorial for any lambda will equal e to lambda. You know that. This is a Poisson distribution distributed with lambda. Not understand?
Example.
There's no need for real world examples. We can just come up with whatever we want. We just have to model it that way. So we just say the probability at k would equal to that. Yes. This is not. Actually, I think that k may be fixed. No, it's not fixed. It actually take on all those possible values. A lot of real examples require Poisson distribution. Okay. Now, is there anything we missed? No. Excuse me? Oh, expected value. Expected value is the way they say, oh, the mean. But the way they define it here, the expected value of a discrete random variable is equal to the probability, the sum that's enumerated, 0, up to, let's say the number of outcomes is n. They can be infinitely many. But it's countable. Has to be countable. That's why this formula works. It's going to equal to the probability at k times, let's see, times k. So if you think about it, so the expected value of some of these distributions, they're already set. So geometric probability, the expectation of a geometric random variable is equal to, let's see, this guy's going to be sum of k equals 0. Probability times 1 minus p to the k to the m minus k. Yeah. It'll be already set. And you can actually derive the probability, the mean of the distribution. They're already known. You can prove that they're already known. Here's an easy one because I don't feel it. So, for example, Bernoulli random variable. Only 2 outcomes, right? P, and it's either 1 or 2. 1 has the probability of p. So it's going to be p times 1. And 1 minus p has a probability, let's say f2. And that will be an example. You're taking the probability of each possible value and multiplying it by the result. But you have to make sure that you have a mapping from the results to some sort of number. I can't say, what's the probability of green times green? That'd be funny. What's the probability of green times green? So, we also define something called the variance. Now, back in the old ages, long ago, wait, one moment.